Hello everyone, welcome back to Chapter 7, Part 2. We had quite a bit of new material that was introduced during the last video, and so I'm just going to jot some of that down. We have our kinetic energy, and this is going to be the energy associated with the motion of any of our objects. And because kinetic energy, like all energies, is a scalar, we don't actually use the vector of the velocity. Instead, we're using just the magnitude or the speed. As such, the direction that the mass is moving doesn't matter. And then any change in the kinetic energy, K final minus K initial, or if we were to write this out in its full form, that change in kinetic energy is the result of all of the work that is done in the system. And our definition of work is, of course, any change in energy, but we also saw last time that work can be evaluated as a force dotted with the displacement vector. And one of the ways that we can evaluate this is to take the magnitude of each vector times the cosine of the angle that exists between them. And so now, in today's video, what we want to do is look at how we can produce the net work done in a system by adding up all the individual work done by all the individual forces, because this way, in my personal preference, is that it's an easier but also a more detailed version of describing how the network is done. Another way that that can be done is if we find the net force that is acting in a system, and then take the dot product of that with respect to the displacement. And we can also get the net work, but that requires us to actually go through the x, y, z summations of force. This way, I think finding the individual work done by each force gives us a greater understanding of what's happening in the system. So that's what we're going to do. All right. So we're going to put together a system of forces. I'm going to have an applied force that points at some angle with respect to our positive x-axis. Now, in the previous video, we actually showed that having a reference frame isn't actually necessary to solve for the work that is done. The only thing that we really need is to see what the angle relationship is between any force and displacement vector. And that shouldn't necessarily depend on what the reference frame in our system is. If I'm expecting this mass to move to the right, well, it shouldn't matter how I set up my reference frame, because the angle relationship between that force vector and that displacement vector is not going to change just because I choose a different reference frame than someone else. But I'll just keep the reference frame there. It's always a good idea to have some kind of a reference frame in the system, even if we don't necessarily need to use it. And this force, we will say that it has a magnitude of 50 newtons. We'll have a displacement with magnitude 10 meters, and we'll provide a mass of 2 kilograms for this object. And so to find the net work that is done in this system, it's not necessarily going to be just that applied force. We need to consider all of the forces in this system. And we know that for this mass, as it sits on this tabletop here, there will be some weight. And because the mass is pressing into the tabletop, there will also be a normal force. And perhaps there's even some friction. Might as well incorporate some friction now, just to see what's going to happen. We'll go ahead and do this problem without the friction, and then we'll incorporate the friction in a little bit. So we'll start with a no friction case, and then we'll do the same problem again with some friction. Okay, so there's 3 forces here that I can see. And that means we will need to find the work that is done by the applied force. We'll need to find the work done by the normal force and the work done by our gravity force. The combination of all the work done will equal the net work, and that will in turn be responsible for any change in kinetic energy that we see for this mass. So, first force is the applied force. To find the work done, we take the dot product of that force along with the displacement vector. We can evaluate that by taking the magnitude of each vector times the cosine of the angle between them. Now, I haven't defined an angle yet, but we'll put theta right there. Theta is measuring the angle between F and the x-axis, but the displacement vector is along the x-axis, so theta will be the angle between the force vector and the displacement vector. And we'll say that's 20 degrees. So now we have values that we can plug in. We have 50, 10, and cosine of 20. All of that will be plugged into our calculator. 50 and 10 is going to be 500. And then we have cosine of 20, which is going to bring that to approximately 470. Now this is work. Work is a change in energy. Energy has units of joules, and so we have 470 joules worth of work that has been done by that applied force. And as we can see, this came out to be a positive number. This means that the force is putting energy into the mass. As we put energy in, we should see that force start to increase the kinetic energy of the object, and in turn, because our kinetic energy is defined by the speed of the object, then we should see this mass start to speed up. And that should make perfect sense to us, because it looks like that force is going to start pulling the mass to the right. As that force accelerates the mass, we should see the mass start to change its velocity. But we have to figure out what amount of work all these other forces are doing before we can finally make that final conclusion there as to what's happening with the change in kinetic energy. Now we need the work that is done by the normal force, and so we will take the normal force and we will dot that with the displacement vector. And just like all the other evaluations, we need the magnitude of each vector times the cosine of the angle between them. Now, I'm going to use a different angle symbol here because the angle between the normal force and the displacement vector is not the same angle that was between the applied force and the displacement angle, or displacement vector. In fact, the angle between the normal force and the displacement vector is 90 degrees. And cosine of 90 is 0. So it doesn't really even matter what the magnitude of the normal force is. We could solve for it, but it's perpendicular to the direction of the displacement, and so it's not going to do any work. It's 0. Likewise, for the gravity force. If we take our gravity force, mg, and we apply the dot product to it with our displacement vector, what should I use for this angle measure? I'll use beta. But the angle between our gravity force and the displacement vector is also 90 degrees. So we get cosine of 90, which is 0. And so the gravity force doesn't do any work. The only force in the system that is doing work is the applied force. So we do a summation of all those forces. 470 plus 0 plus 0 is 470. That is the net work done in the system. The net work is responsible for any change in the kinetic energy. Because our net work is positive, the final kinetic energy will have to be larger than the initial kinetic energy. And let's apply some values here. Let's say that our mass starts from rest. So we have 0 for the initial velocity. But if the initial velocity is 0, that means that the initial kinetic energy is 0. If the initial kinetic energy is 0, then the final kinetic energy has to be the value of the work that is done. And this means that we now have 470 joules worth of kinetic energy, which can be set equal to the final kinetic energy. We know the mass is 2 kilograms, right there. That means we can solve for the final speed of this object. Again, the kinetic energy is a scalar, so it doesn't actually have the direction information involved, but it's pretty obvious that given the direction that that force is pointing, we're going to start seeing the mass increase its velocity towards the right. But the best that this equation can do in helping to solve is to give us an absolute value for that velocity. And that's going to be done by multiplying each side by 2. So that's going to give us, let's see, 940. That actually, let's take this a step back. The 470 is the network, but we can say we have 2 times the net work divided by the mass, and then we have to square root everything. So the magnitude of this will be the final velocity magnitude of our mass. So we have 2, we have the net work, the mass is 2, so those are going to cancel. We get the square root of 470. Back to our calculator. Square root of 470 is 21.7. Alright, so there's our final velocity. After applying this system of forces to our mass of 2 kilograms over a displacement of 10 meters, this will be the final velocity of that object. Now, again, we could solve this same problem by using a sum of forces approach. We could find the acceleration along the x direction. We could then plug all of that information into the appropriate kinematics equation. But the nice thing about using the work energy theorem, the work energy theorem is this expression right here, which says the change in kinetic energy is the result of the net work. Well, there's really only 2 equations that we have to remember. We have to remember that work is found by taking the dot product of a force and the angle that exists between them, and the kinetic energy of an object is 1/2 the mass times the velocity squared. From there, well, it's not too hard to do a summation. A summation is just adding up values. Well, we were able to do that. We applied the dot product 3 different times to 3 different forces, and we found out how much work they did. Once we had the net work figured out, we applied that to the change in the kinetic energy. Well, a change in kinetic energy is just a subtraction problem. And so if we can remember just those 2 equations, then we don't have to bother with a sum of forces. We also don't have to bother with going back and trying to remember which of the 5 kinematic equations we need to apply to the problem. So this is a very simple, condensed method of figuring out what's happening in these systems. Number one, without having to hunt down the different kinematic equations that we need, but also because everything here is now in a scalar form. Okay, same problem, but this time we're going to try it with the friction force. So we'll come back to our diagram here, zoom out just a little bit. Same applied force, same displacement, same mass. We'll even keep the same angle for the applied force. But now there's going to be some friction. And we will assume that there is enough of an applied force to overcome whatever static friction is present in the system. So we will assume that this mass will start to move. And we'll use a kinetic coefficient of 0.1. Now, we can already see that this mass is going to be moving to the right. That is established. We know that friction will oppose the direction of motion. That means we need a friction force pointing opposite the direction of our displacement vector. As for all of the other forces in the system, well, we don't have to recalculate the work that is being done by the applied force, or the normal force, or the weight. We've already done that. The only thing that we have to do is we have to include any work that was done by the friction force. So I'm going to get rid of all the stuff down here because we're going to have to add the contribution of friction to our problem. Let's see here. Get rid of this stuff right now. So now we need the work done by our friction force. Okay. Work done by any force can be found by taking the dot product. So we have a friction force, F of k, dotted with the displacement vector. That can be evaluated by taking the magnitude of each vector times the cosine of the angle between them. Now, I've been using different angle symbols all the way through here. What other symbol could I, let's try alpha. So alpha is the angle between our friction force and our displacement vector, but those are just pointing in opposite directions. That means we have cosine of 180. Cosine of 180 results in a -1. We have the magnitude of each, and so the work done is equal to negative FKD. We know that the displacement is 10 meters, but now we need to know what the value of that friction force is. Back to chapter 6, where friction is fun. Kinetic friction can be evaluated as the coefficient times the normal force. We're using a coefficient of 0.1. To find the normal force, we need to come back and look at our diagram. And we'd probably be very tempted to jump the gun and say, oh, well, normal force is equal to weight. But that is incorrect for this problem. The normal force is based on how much the surface has to push back on the mass. And that means we have to consider all forces or components of force that are acting along the vertical direction. The applied force has a vertical component, and that will contribute to the sum of forces along the y direction. This is a critical aspect of how much work is going to be done by that friction force. So let's take a moment right over here. We'll put together a sum of forces along the y direction. So now our reference frame is actually coming in handy. If we take a sum of forces in the y direction, we have our normal force pointing up in the positive direction. We also have this component of the applied force pointing up in the positive direction. This component is opposite of the angle theta. Theta is the 20-degree value of our applied force. And so we have plus F sine theta minus the weight. Minus the weight. That's it for all the forces in the y direction. So they must add up to give us the net force for the y direction. And that has to tell us how our mass is going to accelerate in the y direction. But all we should be doing is just dragging this mass across the floor. The only displacement that we're expecting is in the x direction. We shouldn't have any motion in the y direction. In other words, we should be maintaining contact with the surface. The only way that can happen is if the acceleration in the y direction is 0. If everything now equals 0, that means that the normal force has to equal the weight minus the vertical component of our force. That is what we get to plug in for our friction force. We have the weight, mg. Let's just take a moment and we'll get a number for this. We have mg, so that's 2, 9.8 minus 50 sine of 20. And I'm hoping I haven't produced a impossible problem here. I'm hoping this doesn't lift the block off of the table here, but we'll find out. We've got 2 times 9.8 is 19.62. And 50 times sine of 20. Whew. Good. I did not make an impossible problem. All right. 19.62 minus 17.1. That gives us a difference of 2.52 newtons for the normal force. That value will be brought down and applied to our friction force. Normal force times coefficient of 0.1. We now have a friction force of 0.252 newtons. That value will be brought into the work expression for the friction force. We have negative 0.252 times the displacement of 10. So we have work done in the amount of a negative 2.52 joules. So not a whole lot, but do note that the work done by the friction force is negative. Friction forces will always oppose the direction of displacement. And so our friction force will always have to do negative work. You should never have a friction force that does positive work, because positive work implies that energy is being put back into the object. And this would imply that the object is increasing its kinetic energy, or that it's going faster. That's not how friction works. Friction does not make things move faster. Friction slows things down, hence the minus sign. Okay, so we have work done by the friction force of negative 2.52, and that will have to be combined with all the other work done in the system by all the other forces. And that will give us the net work. 470 plus 0 minus 2.52 makes for 467.5. Roughly, I'm just rounding that. The net work is responsible for any change in kinetic energy for the system. Now, I erased it, but if we still want to work off of the impression that this mass started from 0, then we can say that the initial kinetic energy was still 0. And that means that all of the work done by all of the forces has to go into the final kinetic energy of our object. As such, our final kinetic energy is now 467.5. We can use that to solve for the final velocity of this object. And in this case, the final velocity is not going to be all that different from what it was without the friction. And that's just because the friction really isn't providing much resistance. But we'll go ahead and solve for it anyways. We've got the same equation as what we did last time. This is the nice thing about having general solutions, is that the general solution doesn't change. All that changes is the values that you insert into the general solution. 2, 467.5, and then the mass was 2. Okay, so 467.5. We need the square root of that. And that comes out to be 21.62 meters per second. Compare that to the final velocity that we had without friction. So without friction, the final velocity was 21.68 meters per second. So not a whole lot of a change there, but we could definitely see a greater change in the final velocity if we had this sliding over a much rougher surface. I just picked a very small kinetic coefficient because I wanted to make sure that this friction force wasn't going to overcome any of the other forces in the system and bring us to a halt. But that could very well happen. But you know, if we wanted to change out the surface, maybe make this 0.9 instead of 0.1, how would that affect things? Well, we would come down to our friction expression, and we would change this to a 0.9, which would change that to a 2.268, which would change this to a negative 22.68. This would be 2.268 now. And then that would make this a negative 22.68. So I'm just following along by changing the values. 22.68 for the friction force. Take the difference in that with the work done by the applied force. Whoops, I got my sign notation wrong here. Redo that. Now we get a net force of about 447. So we've placed this mass on a much rougher surface of 0.9 for the kinetic coefficient. That's causing work done in the amount of negative 22.6, etc. joules. We've brought that into the sum of all the work. And so now if I only have 447 joules worth of work done, that would result in a final velocity of 21.1. So still not much of a change, even though we increased the friction coefficient by a factor of 9. But there will definitely be some systems where I actually had a pretty large magnitude of applied force here, but that was intentional because I wanted to make sure that this thing would not stop as it was sliding. But this is a fairly straightforward example of how the work energy theorem works. We take the summation of all the work done by all the forces, find the net work, apply that to any change in kinetic energy, It's also worth noting that we did not have to use an initial velocity of 0. We could have used an initial velocity of anything, maybe initial velocity of 2 meters per second. What that means is that the initial velocity would not have been 0. It would have been, let's see here, well, we had a mass of 2, and if our initial velocity was 2, well, there's a lot of 2's here, so we got, okay, 4. That would have been the initial kinetic energy for the system, 4 joules. Okay, but does having an initial kinetic energy of 4 change the fact that all of our forces are still doing the same amount of work? And the answer is no. We're still going to have the same amount of work done. The only thing that's going to be different is the final value of our kinetic energy. If we started with 4 joules of kinetic energy and we increased that value by 447 joules, and this we're still considering the high value of our kinetic coefficient here. That means that we would now have a final kinetic energy of 451 joules. And so that would carry through the math, and it would give us a final velocity that is larger than any of the other values that we had before, because we started with a higher initial velocity in the problem. Well, this would be a good place to stop for this particular video. When we come back, I want to take a closer look at this evaluation of the dot product, because this method works really well if you know the magnitude of each vector and the angle that exists between them. But what if you're missing one of those critical pieces of information? How do we find out how much work is done in that case? So that's what we'll look at for the next video, and we'll see you then.